All right. What I want to do here is just go through another example. Okay, another example of how to apply the first law. Okay, just another example of this. And then after we're done with this, then you'll have an opportunity to do one on your own as well, actually with your groups. Okay. So let's take a look at this and read this problem. A frictionless piston cylinder device initially contains 50 liters of saturated liquid refrigerant 134A. Okay, now first of all, refrigerant 134A, we haven't used it much. You may have seen it in the homework, but we have tables for that. Okay, refrigerant 134A is a very common refrigerant. When I was in engineering school, we did have a little bit of tables with this, but oftentimes we were instead using refrigerant 12. Now, refrigerant 12 is commonly known as Freon. Okay, you may have heard that term Freon. But you may also know that Freon is not good for our ozone layer. It's not good for the environment. Okay, it hurts the environment. Therefore, it was banned. Okay, our government banned it and said, no, can't use refrigerant 12 anymore. So somebody came up with refrigerant 134A. I don't know what happened to refrigerant 13 and all the way up. No, that's another story. But refrigerant 134A is pretty common, and good news, it doesn't hurt the environment too bad, so it's commonly used, okay, in lots of applications, okay? And so that's, refrigerators, air conditioning systems, things like that, okay? By the way, there are other refrigerants used in large industrial refrigerators and systems. May not use refrigerant 134A, but instead use refrigerant 12. It's not refrigerant 12. Ammonia. They use ammonia because ammonia is a lot cheaper than 134A. Okay. But what's the problem with ammonia? Anybody know? Yeah, I don't know about its reaction with copper. But I do know its reaction with our human bodies. It's it's poison. Okay, it's poisonous. Yeah, ammonia is not safe. Okay, not that I would go ahead and be drinking 134A, but it's not nearly as poisonous as ammonia. Okay, and so that's why we don't have ammonia in a lot of our home systems, because if that were to escape, you'd have poison gas, and that would not be good. So we, in home systems, we typically use this 134A or something close to it. There's another one that is used that has similar properties to 134A. All right, that's enough of that. The piston is free to move, and its mass is such that it will maintain pressure of 900 kPa on the refrigerant. All right, the refrigerant is now heated until the temperature rises to 60 degrees Celsius. Calculate the work done during this process. All right. First thing we need to do is talk about piston cylinder devices a little bit more, all right? You have one of them in your homework, by the way. I believe it's problem number 3 in your homework is a piston cylinder. So let me draw my little mock-up of a piston cylinder. Here's the piston. Okay, inside the cylinder is gas at pressure P, okay? And we know that gas at a pressure, whatever that pressure is going to push everywhere it goes. Gas at pressure wants to push out. And it's also going to be pushing up on that piston, all right? It's going to be providing a force upward on that piston. What is going to be the upward force on that piston? We know it's pressure P times what is going to give me that upward force? Cross-sectional area, right? Because pressure is force divided by cross-sectional area, right? So if I want to know the force, it's pressure multiplied by cross-sectional area, okay? So that upward force is pressure times cross-sectional area, okay? Where I just call it cross-sectional area A, right? Now, lastly, that's not really the only pressure it feels. Outside of the cylinder, the piston feels a downward pressure from the atmosphere, most likely. Now, it could be some other the cylinder could be inside another cylinder or something like that. But let's just pretend it's the atmospheric pressure. Okay? The atmospheric pressure is also pushing down on the piston from the outside. Okay? And lastly, so that's a downward force. We call that a down. There's really two downward forces. There's two downward forces. There's the atmospheric, I'm going to call it PATM for atmospheric, times the cross-sectional area. But there's also one more thing. The piston itself has weight, right? It has mass, therefore it has weight. We'll call it weight W. Weight W. So it would be a weight plus the weight of the piston, right? The weight of the piston itself. The piston will just naturally fall down, right? So it has its own weight, plus it has atmospheric pressure on top pushing down, okay? So what you have here is a balance. You have here is a balance, because if the piston is not moving, it must be in balance, what you learn in statics, right? The amount of forces up must be the same as the forces down. They have to be in balance. So that's simple. That just says that the pressure times the cross-sectional area must equal the pressure atmospheric times the cross-sectional area plus the weight. All right. Okay. Now, I'm going through this whole process to explain a fairly simple point. I could just simply say it, but I think it's better for us to have a little bit of an understanding. What happens here, let's say you've got this piston and it's just sitting there, nothing's happening. What happens if the pressure inside the cylinder increases by a little bit? What's going to happen to that piston? It's going to move up, right? It's going to move up. All right. Now, what happens when it moves up? What happens to the volume? It increases, right? Then, when the volume increases, what do you think is going to happen to that pressure? It's going to drop. Yeah. And what's going to happen is that it will expand, but then the piston will stop again. Okay, the volume increase, the pressure will drop back to where it was. Now, notice I have a balance here. The pressure inside times the cross-sectional area equals the pressure atmospheric times the cross-sectional area plus the weight. Take a look at the right side of this equation. Will the weight of the piston change? No. Will the cross-sectional area of the cylinder change? No. Will the atmospheric pressure outside change? Not really. Okay? Yeah, sure, a front could come through and we could drop pressure a little bit, but that's negligible, right? Okay, none of that changes. If none of that changes, the pressure inside that cylinder doesn't really change. It is a constant pressure process when you have a piston cylinder assembly. Because if the pressure gets bigger, all that happens is that it expands, but then the pressure will drop again such that it will create that equilibrium right here. Same equilibrium. Okay, you'll always have that equilibrium. What I'm saying, a long way of saying this, is that when you have a piston cylinder assembly as shown, we can make the following assumption. Remember, assumptions are important. One, it's a constant pressure process. Okay? Now, some of you in your minds are thinking about this, and you're saying to yourself, hold on, I don't know if I really believe that, because if that piston goes up, you told me that if the pressure goes up, the piston goes up. Yes, right? And then the pressure will drop down. But what about in that little bit of time when the piston goes up? Isn't that pressure higher to create that piston to go up just for a little bit, and then it goes back down? Yeah, it's true. Okay, is it, but remember this is an assumption, okay? We call this as a fancy thermodynamic term, we say it's a quasi-equilibrium process, okay? Basically it means It's pretty darn close to being equilibrium, and it's pretty darn close to being constant pressure. Yes, the pressure will jump up a little bit and down, but not much, okay? You know, it will change a little bit, but not much, all right? Okay, because as soon as the pressure goes up, the piston goes up, the pressure goes back down, you're back to the same situation, okay? So it's fundamentally basically a constant pressure process. All right. Now, any other assumptions you want to make about this problem that you're reading? Anything else if you think about assumptions like we did before, or anything you want to ignore in the first law or anything like that? Or anybody? Assumptions, because we got to make assumptions. We got to narrow this down. Anybody? How about kinetic and potential energy? Yeah, just like every time it seems like we're just going to say the kinetic and potential energy is equal to 0 because we don't have any information in this problem. I see no velocities, I see no distances, I see no elevations, right? There's no elevation change, there's no distances. Now some of you might say, hold on a second, Dr. Reynolds, you're telling me that this piston goes up. If the pressure goes up, the piston goes up. Isn't that a change in the potential energy of the piston? You would be correct. It is. So isn't that a bad assumption? Potential energy equals 0? Well, it depends on what you mean by bad assumption. Yes, potential energy effects are happening, but I bet they're very small. Okay? I bet they're very small. And oh, by the way, they didn't even give me the weight of the piston. So if they don't give me the weight or the mass of the piston, how am I supposed to even calculate any potential energy? Because remember, potential energy is mgh. I got to know the mass of the piston. I don't know what that is, so forget it. You know, we don't have any of that information. Okay, so I'm always looking for kinetic and potential energy, and most of the time I'd like to get rid of them. I'd like to say they're 0. Okay, unless they're giving me a velocity or they're giving me an elevation, I want to just say they're 0. Okay, and we know it's a constant pressure process. Is there any other assumptions anybody wants to make? Anything about the heat transfer, maybe, or you know, I'm just trying to think of this. Going, is there anything else we want to make, or are we happy where we're at? Any other assumptions? We happy? An you're going to assume this is an isothermal process? You're talking about heat transfer? That would be adiabatic. There's no heat transfer, there's adiabatic. Is there heat transfer or not? Yeah, why do you say there's heat transfer? It's heated. Yeah, so there's definitely heat transfer here. Is it isothermal, meaning constant temperature? I don't know. It says the temperature rises to 60 degrees Celsius. So I think if the temperature rises, it's kind of hard to see it as a constant temperature process. Okay? That's just the pressure. That's the atmospheric pressure pushing down on the piston. I'm just trying to use a point here. We're not going to use that for the problem at all. But I'm just trying to make a point that when you have a piston cylinder, you have a constant pressure process. Okay? That's really the point I'm trying to make here. But atmospheric pressure is pushing down on that. It's pushing down on us, too. We have air on top of us right now, pushing down on us. Okay, I don't think there's any other assumptions that I can see straight up that I want to look at. I'm sure there's others that we could do, but you know, I think that's it. By the way, you'll notice that it says things like frictionless, free to move. Why do you think it says that? Yeah, well, yeah. So what that's really implying, yeah, there's no loss of energy due to friction. It's free to move. It basically again says that it has a constant pressure process. If there were a lot of friction in the piston, as the pressure increased, it might not move, right? The piston might not move because there's so much friction, the pressure could increase and it might not move. But we're saying, nope, the piston will move as the pressure increases, therefore it's a constant pressure process. So that's all that's saying. When it says stuff like that, that's really all it's saying. All right. And by the way, it kind of even tells you it's a constant pressure process because it says that will maintain pressure of 900 kPa. If you look at your homework problem, it says constant pressure process twice in the problem, just so that you know that. Okay? We're trying to be real explicit All right, good. So if it's a constant pressure process and it asks me to calculate the work done, what's the first thing I'm going to think of? That equation right here, this equation. If you see constant pressure, or you figure out in a problem that you have constant pressure, the first thing I want popping up in your head is this. Because you have a pretty good chance you're going to use that equation. Okay? Just as a side note, I'm going to add something to this equation just to try to give a little more clarity. And this is what your text does it sometimes too. I'm going to add a little b there. That little b basically means boundary work. Basically, that's thermodynamic work, okay? That doesn't mean that all work is this way. Remember, there's more work than just thermodynamic work, okay? There's other types of work. Remember, there's electrical work. There's paddle. You could have a paddle wheel work. You could have mechanical work. You could have electrical work, and you could have thermal work. And you'll see occasionally your textbook put a little b in there. That means thermal work. Okay, it's boundary work. Okay, that's thermal work. Okay, but that's key here because that's what we got. Okay, all right. So all we now have to do is figure out P, V2, and V1. The good news is 2 out of those 3 things are given to me in the problem. Okay. What's P? 900 kPa. Good. What else do I know? I know the volume at state 1, right? It says a frictionless piston cylinder device initially contains 50 liters of saturated liquid refrigerant 134A. Now I can write volume equals 50 liters, but honestly the only thing I care about in liters is when I'm drinking a 2-liter of pop, because I don't usually deal with liters any other way, okay? I'm probably going to want to convert that, okay? The good news is liters has a very easy conversion, okay, to meters cubed, okay? 1,000, yeah. 1,000 liters, that's a whole lot of pop. That's like 500 2-liters. Somebody bring that into your next party, okay? That's a lot of 2 liters. 1,000 liters is 1 cubic meter, okay? So if you have 50 liters, you work it out, you've got 0.05 meters cubed. So we have 50 liters. We have 25 2-liter bottles of saturated refrigerant 134A. Okay? So, boy, if I could just get V2, I'd be set. All right? Because this is the answer. Calculate the work done during this process. If I could get V2, done. That's it. That's the work. I got to kind of know it's a constant pressure process. I got a simple equation. I can put this stuff in and bang, get it out. Okay, so how am I going to get the total volume at state 2? Okay, well, maybe we need to start writing down what we know about each part here, okay? What do I know about state 1? I know it has 50 liters, but what else do I know?
Saturated liquid.
Saturated liquid, good. So it's sat liquid, and it is, and I know I have 0.05 meters cubed, that's the volume. Good. Now, let's write, before we get into anything, what do we know about state 2? Yeah, and oh, by the way, here I have a pressure, right, of 900 kPa for state 1, and I also have a pressure of 900 kPa for state 2, right? Same pressure. Anything else I know about the final state?
60 degrees C.
That's right, 60 degrees C. Great. Okay. So anybody got a strategy for me to get? I need to get the total volume. Now I know this. if you give me two things, I can look up stuff in the properties. And if you give me two things like here in state 2, I think I can get the specific volume of state 2, right? I think I could do that. Let's do that one. Let's do that first, okay? So let's go to our tables. I'm going to pull up mine here. Okay, so here's my table. And now don't go to water now. We got to go to refrigerant 134A. I think I went too far. Here we go. Here we go. We're getting somewhere. Now, where am I going to go to first? There's two things I know. I know it's 900 kPa and I know it's 60 degrees Celsius. I'll go to the 900 kPa. Okay. So if I'm at saturated refrigerant 134A and I'm on the pressure table, okay? That's table A12. And I know I'm at 900 kPa, my saturation temperature is 35.5 degrees Celsius. So what does that tell me where I'm at? If I am at 60 degrees Celsius for 900 kPa, where am I at? I'm not unsaturated, right? I'm what? Superheated, right? Because my temperature is greater than the saturation temperature for the same pressure, okay? So I'm superheated. So I got to go to my superheated tables, and I got to find 900 kPa, which, oh, by the way, is 0.9 megapascals, 0.9 MPa. And then I got to find 60 degrees Celsius, and if I look real careful, I found it. Let me circle it. Okay? 60 degrees Celsius for the 900 kPa, 0.9 MPa. The specific volume is given there as 0.026146. Okay? 0.026146. So hopefully you know how to do that in yours. 0.026146. So I'm going to write this here. I don't know if I really have to write that many decimals, but I did. Meters cubed per kilogram. Okay, got that. But how do I get the mass? Yeah, I don't know anything about the mass given in state 2, but what could I do at state 1 to help me solve for the mass? Yeah, what I could do is this. Remember that the volume, that the specific volume, right, is equal to the total volume divided by mass. Therefore, if I want to solve for mass, I can manipulate this equation and say mass is volume divided by specific volume. Well, I know what the volume is, so if I could get the specific volume at state 1, seems like I could use that very simple equation and get the mass, right? Okay? So let's do that. What's the specific volume of saturated liquid at 900 kPa? Because that's what I know about state 1. It's saturated liquid 900 kPa. So I'd go back to my tables. Okay. And I'm going to go to 900 kPa again, where I was before. And let's see if I can, okay. The saturated liquid is given as the first number after the temperature, right there. Saturated liquid, 900 kPa. It looks like it's 0.000858. 0.000858 for the specific volume of sat liquid. 0.000858. Meters cubed per kilogram. That's the unit. So then, looks pretty easy for me to solve for the mass. The mass is going to be equal to the volume at state 1 divided by the specific volume at state 1. That's going to be 0.05 meters cubed divided by specific volume which is 0.000858 meters cubed per kilogram. And somebody help me, what do I get? 58.28? 275? I'll just say 3. 58.3 kilograms. You can keep your numbers on the calculator, but I'll just write 58.3. Then what is the volume of 2? Well, the volume of 2 is going to be the mass times the specific volume of 2, which is going to be 58.3 kilograms multiplied by 0.026146, right? And again, that's meters cubed per kilogram. We just pull that number down. And what is the value? Something like 1.15 or something? I don't know. Kilograms? What's that? 1.523. So something 1.524 kilograms, something like that. About 1.5 kilograms. Oh, no, kilograms, right? Kilograms, yeah, kilograms. Oh, sorry, yeah. No, you're right. Sorry, you're right. Meters cubed. Yeah, I'm not looking at my own units. Meters cubed. You're right. I'm thinking about mass. Meters cubed. Yeah, meters cubed. Okay. So now we got everything, right? We've got my volume 2. I've got my volume 1. I've got my pressure. I got everything. This is just plug and chug at this point. To calculate the actual work during this process, I multiply 900 kPa times V2 minus V1, 1.524 minus 0.05. That's going to be meters cubed. Now, if you work out the units, a Pascal is a Newton per meter squared. A Newton per meter squared multiplied by meters cubed gives you a Newton meter. A Newton meter is a joule. Now I have a kilopascal, so this answer will be in kilojoules. Looks like it's going to be around 1350 or so. 1326.6. We'll just say 1327. About 1327 kilojoules. There's your answer. Yes. That's why I would tell you as a tip, pressures, if they're given to you in kilopascals, that's nice to keep them in that, because then if you multiply by a volume, you're going to get kilojoules. If you have pressure in megapascals and you multiply by a volume of meters cubed, you're going to get megajoules. So as long as your volume's in meters cubed, you can do that. That's kind of nice. What's that? That would be power. This is energy. This is the work. Work is just energy, which is in joules or kilojoules or megajoules, or BTU for an English unit, which we will do sometime to time. Before I finish this problem, one more thing I want to do. I want you to visualize this problem on a PV chart, because one thing that you're going to need to do at least once on the exam next week, Thursday, is draw one of these PV lines. Okay? So there's the dome. We're going to do this easy. Pressure versus specific volume. What would this process from 1 to 2 look like on a PV diagram? Well, it's actually pretty simple. This is a constant pressure process. So the line has to be a horizontal line because it's constant pressure, and pressure is the vertical axis, right? And it starts out at sat liquid. So you just kind of pick a point right there, saturated liquid, and then the pressure goes like that. It ends up over here in state 2 as superheated. It starts out as sat liquid, so it's right there on the left side of the dome, but then it crosses over into the superheated range for state 2. So that's a little PV diagram showing that process. Okay?